Hi everybody, I'm Mr. Auerbach. I'll be your chemistry teacher today, and today we're going to continue our discussion of valence electrons, ions, and ionic bonding. Okay, so yesterday we were talking about how you have valence electrons, which is the proper term for the electrons in the outer shell of an element. And so, for example, we had sodium, which has one outer electron, and it will want to lose that electron because who's the happiest elements on the periodic table? The noble gases. That's right, because they have a full valence shell. All of them are very happy, and everybody wants to be like them. And if sodium could just lose that 3s1, sodium doesn't feel like it's cool enough. Sodium is cool enough, but it thinks it's not. It's really kind of unstable, actually. Like many of us. Sodium's kind of unstable because what sodium has underneath this... Okay, everybody quiet now. What sodium has underneath this 3s1 is a full inner shell, which would be the 2s2, 2p6. I'm sure you can't see this at home, but you should have come to class. Okay, but what it has underneath, if it could just lose this single electron, then it would have the outer configuration of neon, which would make it very happy and stable, and so that's what it does. It will lose that electron. We've discussed this. This is review. And so it becomes like neon, but also, what else happens to it? People who were here yesterday, which is all of you.
Positively charged.
It gets a positive charge, yes, correct. Because it goes from having 11 protons, 11p plus, and 11e negative. Instead, it loses one electron, and it becomes... It then has 10 electrons, which gives it a total charge of +1, because 10 electrons and 11 protons leaves one positive charge left over. So it becomes the sodium +1 ion. And that's all well and good, but this never happens by itself. This doesn't just sort of happen spontaneously. Sodium is a soft silvery metal. And it's not going to just sit there and lose electrons. In fact, you might think, well, if you just put it into water, maybe it'll lose electrons. If you put sodium metal into water, it'll react with the water, and you'll get this explosive reaction, and that also is not going to cause it to ionize. What actually has to happen is there has to be somebody there who will take that electron. For example, chlorine. I know this is kind of review, but let's talk about chlorine a little bit. We'll put sodium's electron back for a second. We'll give it back its outer electron, and never mind about the... Well, just pretend that +1 isn't there. Okay, and chlorine is over here in column 7A, and it has 7 outer electrons, S2P5, only 1 electron away from real, true happiness, and so there's 2, there's 4, here's 2 more, and here's 1. And so chlorine's just hanging out and wishing it was stable, like all of us do. And here comes sodium. How you doing? Sodium and chlorine start to talk, and they realize that they might be able to help each other, because sodium's like, hey, I see you're missing an electron. And actually, even before sodium can say anything, chlorine takes it. Chlorine is what you call very electronegative, meaning it has a very large attraction for electrons. So and sodium is perfectly willing to give that electron up. And so that's what happens. It's not a sharing situation. It's not a loan. It takes it. Chlorine takes it right up, and then goes from being 3s2, 3p5 to being 3s2, 3p6. Very happy, very stable, but also negatively charged, because it has gone from 17 positive protons, 17 negative electrons, to losing one, or gaining one, excuse me, sorry. Okay, it has gone from 17 to 18. Sharpie markers, irritating but superior. And so now, with 18 and 17, it has one extra negative charge, and it becomes the chlorine -1 ion. So now we have a situation where we have +1 and -1. It's a match made in heaven, since they were already so close to each other because of the electron exchange. Then they simply attract each other, and they are now together. Both of them with what they call their full octet. That's the word of the day, is octet. Because, why do we use the word octet?
Full outer shell.
Full outer shell with 8 electrons, right. Octet, if you think about it, the outer electrons are always S and P electrons, and so full outer shell is going to be 8 electrons, which we've discussed a cajillion times at this point. But sodium has a full octet now because it lost that one. Now it has the full one underneath. Chlorine has an octet now because it gained that electron, and now, even though it has a charge, it still has the full shell. Okay, so that's basically review from yesterday. But now it's on film, so it's official. Alright, so that's all well and good. But what if we were to talk about somebody like magnesium? Okay, so here's magnesium, okay? And magnesium is going to make a +2 ion. Why is magnesium going to make a +2 ion? Because it loses 2 electrons, yes. It loses 2 electrons, not a trick question. And awkward silence. But yes, magnesium will be +2 because it goes from having 12 protons and 12 electrons to then having 10 electrons, because it has 2 outer electrons, and here they are. And when it loses them, it's going to form a +2 ion because it has 2 less. It has 2 less electrons than protons. I talk too fast for my brain sometimes, and I have to stop and catch up with myself every once in a while.
Your camera's not very centered.
It's not what?
It's not very centered. It's leaning a lot towards that way.
Is it showing this area?
Yeah, you can barely see you. You can barely see you for most of it.
Well, I'll have to remedy that. No, that's okay. I don't care. I just wanted to see magnesium and chlorine. Everybody sees enough of me. And not enough magnesium and chlorine, Lord knows. Alright, let's take chlorine back to its original state, though. Before it was an ion, we'll take away that. Okay. We'll take away that -1 and we'll take away that P6. We'll make it back to P5, only old P5. Remember when I was P5? Huh, the good old days. Before I got that electron. Okay, I'll edit that out. So what's wrong with this picture? What is wrong with this picture? Because magnesium wants to lose 2 electrons, and chlorine seems to be perfect. It wants electrons, magnesium has electrons. What could be wrong? What could go wrong with this? What could go wrong with this? What's the problem? What's that? Right, the chlorine just needs 1. So chlorine takes that electron because chlorine's electronegative, very good at attracting electrons, but what's wrong with this picture? Magnesium's got 1 left. And this isn't like a lot of things in life where you do the best you can and then you just sort of limp ahead with life, much, like here. It's all or nothing. Magnesium's not going to be like, okay, I'll take 1 electron, or I'll get rid of 1 electron, and me and this chlorine and my extra electron will just go, limp around and be all weird and hope to run into, somebody to take this other electron. It doesn't work like that. It's all or nothing. Either the reaction's going to happen or it's not. And so what do we need? Let me get these out of the way. now that we've talked about this already, what do we need to make this work?
Another chlorine.
Another chlorine. That's right. Look at this! Whoa!
Or another valence.
There we go. Here's another chlorine. And I don't have 7 more electrons to demonstrate this for you, but we know that chlorine wants that electron, and so here's going to go another chlorine, and it's going to, here, I'll tell you what, I'll draw the other ones in. In Sharpie, that's right. Can't stop me. And so now, here comes this chlorine, and now we've got some octets going on. We've got this, here, here, stay. And we've got this here with 8. Everybody's got their octet. Magnesium has its octet underneath. So we have -1, put that over there, +2, and -1. What you need to look at is, as long as you add the cation, by the way, that's what you call a positive ion. And does anybody know the word for the negative ion? Anion, that's correct. Now, if you, for me, this is, okay, when I was 17, literally your age, most of your age, I used this to remember it. I like cats. I feel very positive about cats. They give me a very positive feeling. I'm not kidding. That really is what I did, and it really has worked for, I don't want to say how many years. Many, many years. I have positive feelings about cats. Yes? Whoa. Yes, it does. Cat, I mean, the same root. Positive, cat, plus, adding, and, negative. Yes, catabolic is building up. Anabolic, is that true? Anabolic is breaking down. I hope that's right. I'm on tape saying that. Is that true? Catabolism, anabolism, and catabolism. Crap. No, you know what I think? I think catabolism is... We'll return in just a minute after a word from our sponsors, anabolism and catabolism. Today's lesson is brought to you by the letter CL. Okay, I don't remember which one is which. Isn't that pathetic? That's okay.
Wait, what about your statement, though?
What? I'm sticking with, see, this is why I went with cats are positive, and if you have somebody named Anne in your life that you don't like, then you can think of it that way. Negative feelings towards that person. Okay, let's get on with our lives. What I was trying to say is that as long as the cation and the anions add up to equal and opposite charges, then you are in good shape. You have a valid compound. By the way, how would we write this compound? What would be the formula for this compound? Cl2Mg, Cl2Mg. Yes, except that you have to switch it around. Just like the periodic table, metals are on the left, non-metals are on the right. The convention, meaning the way it's always done, is to use the, to put the metal on the left, Mg, and the non-metal on the right, and yes, it would be MgCl2. Remember we use the little subscript to denote how many chlorine atoms there are, and if there's no subscript, that is the silent one in chemistry. Okay, and this always works the same way. So if you had, moving on, taking these away, the last example I'll do here is if we had our friend aluminum, Al. Al is from group 3. Al has 3 outer electrons. Al is going to form what ion will aluminum form? What will be the... I know, but just say it anyway. What? Thank you. Positive 3. Aluminum will form the +3 ion. And so, once again, it will not be satisfied with 1 chlorine or 2 chlorines. How many chlorines does aluminum need? 3, that's right. So I better find another chlorine. Oh look, here's one. Cl -1. So here's another chlorine. So let's just see what really does happen. So here we go back to where we were before. Here's the chlorine with 7. Here's the other chlorine, and here's the other chlorine. Here's Al move them down a little bit. And so, there we go. Whoa. Yeah. Video's starting to drag a little bit now. That's okay. This is the last example. So, the very last thing, what will we call this? AlCl3, says Thomas, and he is correct. How do we say it, by the way? Let's have our first lesson in how do you say these things. The way you say an ionic compound's name is you name the metal. We'll be doing this in another lesson, but this is a preview to our next exciting video. You name the metal completely with its full name, and then the nonmetal you replace. You take the root, which in this case CHLOR is the root, chlor, and you cross it out. You cross out the rest, the suffix in this case, and replace it with IDE, right? Sodium chloride, aluminum chloride, that's how you would say this. If you think about it, there are many other examples, like fluoride. When they say you need fluoride in your toothpaste, what you're really getting is sodium fluoride.
That's actually just what I was about to ask.
Yep. Fluoride. So that's how you name ionic compounds. What we'll find out is that there are many different little weird esoteric rules for naming these kind of compounds, and covalent compounds are even weirder, which we'll learn about next. AlCl3, aluminum chloride.
What did we just learn? What is this called?
What is what called?
What?
Ionic bonding.
We're still on. Okay.
Yes, we're still on ionic bonding. Okay, so the last thing I want to show you, actually there is one more part. We're done over here.
Gotcha.
So, okay, the way that you come up with the formula for an ionic compound, and this is the last thing I'm going to do. First, I'll do 3 quick examples, which we already just saw. If we're using the chloride ion, by the way, just having a minus means -1, just like everything else in chemistry. If there's no number, it's a 1. The examples we did.
You may want to move the chlorine out.
The examples we did were simple enough. You need to combine. You have to figure out the charge of your ions, and then you combine them in a ratio that causes the positive and negative ionic charges to add up to 0. Basically, that's the game. We're playing a little number game. So with sodium, which is just +1, very simply NaCl, because 1 plus -1 equals 0. Magnesium is going to be, let me erase this now. Magnesium is going to be MgCl2, because the 2, well, I'll do it down here. 2 plus -2, which is what you get when you do 2 of these, equals 0. And then aluminum is going to be AlCl3, because 3 plus -3, which is really 3 times -1, equals 0. Okay. Okay, so if we had magnesium, which is +2, and oxygen, which is -2, obviously the compound that's going to be formed, can we see this, hopefully? MgO, because +2 and -2 add up to 0, we've made a good compound. The last one I want to show you, though, is the one where it gets a little confusing. What if we wanted to do aluminum, which is +3, and oxygen, which is -2? Aluminum plus oxygen. What are we going to do now? Because, let me draw these over here actually. Al +3 and O -2. What are we going to do now? Because you can't just have, add more of these or add more of these. Erica is straining to be heard back there.
Oxygen is going to invite some of his buddies over to hang out and take that extra.
Well, that's true, but the thing is, no matter what you do, you have this odd and even number problem. So no matter how many oxygens you have, you're still going to have an even number. So there's one other thing that has to happen.
You have enough of
Ah, if you had another aluminum. What's the word, the mathematical term for what you're looking for?
I don't know, I'm not very good at math.
Lowest, okay, well you're absolutely right. You're good at chemistry. You might not be good at math, but you're good at chemistry. Lowest common multiple. The lowest common multiple that they all go into is going to be the number 6. So you need to be thinking, how am I going to make these, again, be equal and opposite? Positive 6, negative 6. In order to do that, we'll have 2 of these and 3 of these, because 2 times positive 3, positive 6. 3 times minus 2, negative 6. You add them together, you get 0, and we call this compound Al2O3. Okay? So that's pretty much all I have to say about this. As delightful as it's been, we will draw this to a close, and that's it.